Hey everybody, and welcome back to Linear Algebra Online. So today we're going to talk about something called orthogonal diagonalization. And to kind of motivate this, I'm going to work through a problem here. So I'm going to start with this matrix here, and I just want to diagonalize it. Okay, so if you use like eigenvec, eigenval, or Symbolab, or something like that, you're basically going to notice that the vectors are, let's call it like, let's do v1 equals 1, -2, and v2 is 2, 1. And so if you do, where p is just built out of, v1, v2, and then you find P inverse from that. If you do that out, you'll notice P inverse AP is equal to the matrix -3, 0, 0, 2, which is my diagonal matrix. So that would be like how you diagonalize the matrix. And truly, these are the eigenvalues for this matrix right here. In this situation, okay, if you look at the eigenvectors v1 and v2, note that v1 is perpendicular to v2, right? Like you just like flip and negate, one of these, like this one or whatever, and you get this, or flip and negate this, and you get this. And so that means that in, 2 dimensions, these two things are perpendicular, or you can just dot product them and see that you get 0. And so there's something actually nicer going on here. So you could normalize these vectors, okay? So u1, so if I do like u1, which is v1 over the magnitude of v1, you're going to get 1 over root 5, comma, -2 over root 5. And then we could call u2 v2 over the magnitude of v2, which would be 2 over root 5, and then 1 over root 5. And both of those are like unit vectors, okay? So then if you do q just equaling u1 now and u2, this would be an orthogonal matrix. So again, orthogonal matrix being one that is got built out of perpendicular vectors, but also length 1 vector. So really, I wish they would call them orthonormal matrices, but they're called orthogonal matrices. So we know that for these kind of matrices, then the inverse of Q is just going to equal Q transpose, right? And so if we wanted to do this problem a little quicker, okay, you could then do Q transpose AQ, and you never have to worry about, the inverse part could just come really naturally, right? Because you just literally take the transpose of Q, and that should still equal D, like the same old matrix up here. It shouldn't be any different. And it's a good thing to just test if you want. You just, literally take the transpose, and you'll see if you do QTAQ, it's still going to give you D. So these kind of things where we've orthogonally diagonalized a matrix here, computationally are easier than dealing with like having to take the inverse of like a really, really, really big matrix. Basically just because a normalizing computation, which is what this method has, is easier than a inverse computation, which this one has, right? And so it's very reasonable to want to know how, under what conditions we get this kind of thing where we could do this diagonalization versus the standard diagonalization that we're used to. And so that's what we're going to talk about today. So that matrix A is very nice because it is not just diagonalizable, but it's actually orthogonally diagonalizable. And these are basically just square matrices that basically you could do the QT AQ equals D computation. So if there exists a matrix Q such that the diagonal matrix D comes out of that multiplication, then it is orthogonally diagonalizable. And again, the motivation is just because the inverse is really easy to find. And so what we're going to kind of turn to is figuring out when do these show up. There's something nice about the structure of this matrix, and if you look at it, there is something nice that you might think. Also, there's a word on here, which is a big giveaway, but that's what this thing is. So there's a very famous theorem in linear algebra called the Spectral Theorem, and this gives us a very important condition to find these orthogonally diagonalizable matrices. So just a side note, there is this thing called the spectrum of a matrix, and when we say spectrum, I think this was used by it was used by a mathematician named David Hilbert for the first time, but I'm not 100% sure about that. But a complete set of the eigenvalues is what we call the spectrum of a matrix. So, if you have like a 2 by 2 and the eigenvalues are 1 and 2, then the set of 1, 2 is like the spectrum of that matrix, okay? But this theorem says that if you have a square real matrix, and there actually is a complex version of this theorem, but it's much more complicated, no pun intended. So we're just going to be concerned with the real one. But if you have a square real value matrix, so no like imaginary components in there, then a symmetric matrix is equivalent to an orthogonally diagonalizable one. So the fact that this was symmetric, right? Again, just symmetric meaning if you drew like on a diagonal line, then you could like reflect over that line and it looks the exact same. So computationally, it means more specifically A transpose is equal to A. That's what symmetric is. This is basically just saying AT equal to A is equivalent to orthogonally diagonalizable. And so I do want to prove this whole theorem, but to start off, I'm just going to prove the easier direction right now. So I'm going to actually prove the reverse implication. So we're going to assume that A is orthogonally diagonalizable. And what that means, again, is just that QTAQ equals D. And we show AT equals A, or that A is symmetric, okay? And so I'm going to start off. It's very much a kind of matrix, just algebra proof. So a lot of this is just going to be like equivalent kind of equations as I go down. So I'm going to start with this statement, which is pretty obvious, that a diagonal matrix is equal to its transpose, right? You can just flip it around and it's going to look the exact same, right? And so what I'm going to do next is I'm going to use this part. So D is equal to QTAQ. So I'm going to put QTAQ in for D, right? And then, so that's just doing substitution just based on this up here. And then the left side, I'm just going to like copy over QTAQ. Then I'm going to take the transpose on the right. And so I would get, it's like the socks and shoes thing. Basically, the order is all going to like flip left and right kind of. So you get QT, AT, and then QT, T. And so let's just copy the left side down. I'm just going to literally take the transpose of the transpose, which is just Q, right? And then, now it's pretty obvious probably, right? Like I have QT, QT, Q, Q, right? And you could unpack everything, right? If you multiply on left by inverse of QT, which is Q, and on right by inverse of Q, which is QT. And then if you do that, right, of course you would see that we have thus A equals AT, or A is symmetric. So that's just the proof of the reverse direction of the spectral theorem. But very important little thing, that if you see a symmetric matrix, it is going to be orthogonally diagonalizable. And if you have an orthogonally diagonalizable matrix, that matrix must be symmetric. That's just an equivalent statement. Okay? All right, so I wanted to do a proof that involves symmetric matrix and the eigenvalues of it. So I want to prove that if A is a real symmetric matrix, then the eigenvalues of A are actually going to be real as well. So you would never get complex roots from the characteristic polynomial for these kinds of matrices. This is actually tied in very directly with this because it's tied in with this part right here. So A is a real matrix. In order for this equivalence to happen, then you need that, and it's a little more complicated if it's a complex matrix. I took a few different linear algebra courses, and I remember in my upper level ones, like I think I took 2 in grad school, and in those ones, that's when we get into a lot more like complex valued matrices, and some stuff gets a lot trickier. But this is actually going to show like a good proof technique that I just feel like we haven't really seen, so I wanted to walk through the proof of this. All right, so if A is a real symmetric matrix, then the two things that I have basically to work with is that AT equals A, right? I'm going to use this notation, and I'll explain it here in a second. So this is what we have, okay? So what I mean by that is A is symmetric, and A is equal to its conjugate matrix. And so this isn't something that we've seen before, but I can kind of just like explain it over here. So conjugate, I'm literally talking about like in algebra 2, you have like A plus BI, and then the conjugate is A minus BI. So you can do this with vectors and matrices and things too. Like if V equaled, 1, 2, there is no imaginary component there, so it's going to equal its conjugate, right? But like if V, we'll call it 1, and V2 is, I and then 1, then V2 conjugate is going to equal negative I and 1, okay? So, here V2 does not equal V2 conjugate. But we know that A, and you can do these for bigger matrices, a vector is really like a matrix, just a special size one. So there's nothing wrong with doing this for higher amount of entries too. But basically, since A is a real symmetric matrix, this is the symmetric part, and this is like how we show real. So real things in math are just ones that equal their conjugate. Like this is a real valued vector because it equals its conjugate vector. So this is what we have, and we want to prove that, we have that, and we're going to show that lambda equals lambda conjugate for all basically eigenvalues, right? So just arbitrary lambda equals its conjugate. So that would do it. That would show that the eigenvalues of the matrix are real, right? So it's kind of a tricky proof. I'm just going to kind of get into it right now. So I'm going to start off with my standard eigenvector setup, right? So we know we're talking about eigenvalues. We can use that, right? And so from that, we need to bring in the conjugate somewhere. So what I'm going to do is I can just take the conjugate of both sides like this. And if I take the conjugate, you know that it basically that A conjugate is equal to A. And so from that, you can get that A would equal, so you have the conjugate of the vector there, which that part might need to be in the problem. But then we have like conjugate of lambda and the conjugate of the vector. So you can basically, like in a sense, kind of distribute this to both of these things, just apply it to them. And when we apply it to A, based on what we have here, we know that A conjugate is equal to A. We can assume that like V conjugate is equal to V because we don't know anything about the eigenvector and that being real. We just know we want to show the eigenvalues are real, but this isn't necessarily one that we can just write V here. Okay, so these were like arrow vectors, which actually maybe for clarity, let's get rid of those. And then these are conjugate bars. Okay, so that's going to be important. Okay. And then we also probably need something with the transpose. So I am actually going to start with, and this is one of those things that's kind of unclear, I think, until you start kind of seeing where I'm going with it. So V conjugate transpose times A transpose, right, would equal A V conjugate, that product transpose, right, socks and shoes kind of thing. And then based on what I have up here, right, I can take this, substitute in this. So I would have lambda conjugate V conjugate transpose, right? Then I could use socks and shoes again, and I can go back. So V conjugate transpose, lambda conjugate transpose, okay? Now, lambda is just a number, right? So the transpose of a number doesn't really do anything. So I can also just, so basically I'm saying that lambda conjugate transpose is just lambda conjugate. And I can also, because it's a constant, move it in front, just because you'll see later on I want it in front. But, so that's just, this is a representation of what this could equal, right? So now I'm going to actually utilize, I'm going to bring in lambda, okay? So I'm just going to talk about, I don't know, what color do I want here? So we'll just talk about lambda and then multiply lambda by V conjugate transpose V, okay? And this is where I can do another one of these things where I just, like here I passed lambda in front. I can move lambda into the middle, right? So V conjugate transpose lambda V, right? And I'm doing that. Actually, not quite yet. I want to do one more thing, sorry. So lambda V is equal to AV. So now I have V conjugate transpose AV, right? And then I'm doing that because I want to group these two. And we know that since A is symmetric, right, I can actually link now this with my line in blue right here, because V conjugate transpose A could be equal to V conjugate transpose A transpose, right, and then times V, because A is symmetric, right? But then because of this line equaling this, right, I would have then, basically bring this down, and I could say that what I started with there is the same as lambda conjugate V conjugate transpose V. So I did that V in red because it is this same V right here, right? I just subbed out this part for lambda conjugate V conjugate transpose. Whew. Okay, so now, utilizing a very important fact. So we know that things like V conjugate transpose V is the same as V conjugate dotted with V. Right? It's like the duality of transpose and dot products. We get, because of this equaling this, we get that lambda V conjugate dotted with V has to equal lambda conjugate V dotted with V. And so I can subtract and factor out the dot product. So I get lambda minus lambda bar V conjugate dotted with V equaling 0. And note since v is an eigenvector, v bar dotted with v cannot be 0, right? So that means that lambda minus lambda bar has to equal 0, or lambda has to equal lambda bar. And that would prove it for us, right? So that means that then truly, right, we've shown that the eigen values of A are real since they equal their conjugate. And that's just kind of a neat proof, I think. So you haven't really seen many of these or any of these like complex analysis type proofs. Turns out you use these a ton in math all over the place down the road. But it's a very common trick to show that something is real by showing that it equals its conjugate, just because of like what I was saying over here. So I think that's a good one to kind of see how we work through it. Definitely kind of tricky. And like coming up with like some of these clever lines as to like where to start can be really tricky, but I wanted you to see it. All right, so this is another just important result. If A is symmetric, then any two eigenvectors corresponding to distinct eigenvalues of A are orthogonal. All right, so this is a really nice result, just saying that no matter what matrix you have, the eigenvalues of distinct eigenvalues. So, you know, if you have an eigenspace, it's like dimension 2. We're not talking about those because those would be linked to like one eigenvalue. But the ones that link to different eigenvalues, that they should be perpendicular to each other. All right, so here what we have is, so basically we assume A equals AT and show V1 dotted with V2 equals 0 for eigenvectors V1 and V2, which correspond to distinct eigenvalues. We'll call them lambda 1 and lambda 2. So that's the idea of what we're about to do here. So we know we have basically like a setup where it's like A V1 equals lambda 1 V1 and A V2 equals lambda 2 V2. Right? That's just, you know, kind of this idea of having distinct eigenvalues and eigenvectors. And so what I'm going to do is I'm actually just going to start kind of like the last proof. I'm going to pick something kind of weird to start with, but you'll see where this is going, I think, once I get into it. So I'm going to start off with just lambda 1 times V1 dotted with V2. And sometimes in proofs like this, you just want to, if you want to show something like this, you just introduce it and start kind of playing around with some stuff, and hopefully you can get to what you want. So there's a property with the dot product that you can like pull out a scalar if it's in either thing that you're dotting there. So I could also just put it in, right, and still have it be equal. So, whoops, not V2. So I could have lambda 1 V1 and dot that with V2, right? But we know that lambda 1 V1 is AV1, right, dotted with V2. But based on the whole duality thing with dot product, this is then the same as the first thing's transpose times the second thing, right? So this is just the definition of like dot product, the transpose definition, okay? So then I'm just going to go ahead and take my transpose. So I get V1 transpose A transpose V2. Then I'm going to go ahead and regroup some stuff, right? Actually, I think so we know A transpose is A, because A is symmetric, so we're just going to actually put that in right there. Then I'm going to regroup, so I want you to kind of look at this, right? So if you look at that, we know then that's the same as V1 transpose lambda 2 V2, right? Just based on this up here. And so we can take lambda 2 out in front and get v1 transpose v2, but that is, with duality, the same as v1 dotted with v2, right? And so now, if you look at it, right, we get this equals this, right? And we know, I'm just going to say, so lambda 1 minus lambda 2, just like in the last proof, we can like do this factoring, right, and set that equal to 0. But we know that lambda 1 minus lambda 2 cannot equal 0 since lambda 1 and lambda 2 are distinct, right? So v1 dotted with v2 has to be 0, i.e., right, v1 is perpendicular to v2, which is what I wanted to show. So kind of a cool, more, I think, straightforward proof. Basically just cranking your way through a lot of different like dot product duality, transpose stuff, and getting to a point where you can equate the lambda 1 times the dot product with lambda 2 times that same dot product, and then using the fact that since these are distinct, those are not the thing that are getting you to 0. It has to be this that gets you to 0. That's the idea. All right. So I just wanted to show you like a more straightforward problem here. I feel like I've done a lot of proofs in this video. So just given this matrix here, I want to show you that this result truly holds, that if A is symmetric, which that one is, then any two eigenvectors corresponding to distinct eigenvalues of A are orthogonal. All right. So I'm just going to go ahead and use like eigenvec and eigenval. The eigen, if I use eigenvec, okay, we get these for our eigenvectors. So it's one that has, one eigenvalue has geometric multiplicity 1, and the other one has geometric multiplicity 2. And so we just want to see that this vector is perpendicular to these two, okay? So, so actually, I don't like this notation, I just realized. So this should really be like eigenspace 1, eigenspace 2, okay? But I'm going to say this is V1, this is V2, and this is V3, okay? So if you do V1 and you just dot it with V2, notice you get minus 1 plus nothing plus 1, which is 0, which is good. And then V1 dotted with V3, you would get negative 1 plus 1 plus nothing, which is equal to 0, which is good. Now notice if you do V2 dotted with V3, you get 1 plus nothing, which doesn't equal 0, but that's okay. I'm going to put a check mark on that too, because these two didn't have to be perpendicular. The only ones that had to be perpendicular were from distinct eigen values, right? And so this is just kind of a nice property, and actually it's going to tie into like the proof of the spectral theorem, so in the other direction. But yeah, that is an important result. If you have a symmetric matrix, then the eigenvectors of distinct eigenvalues will be perpendicular.